Okay. All right, we're going to get started here in a few minutes. It's 5 o'clock. I just want to make sure everything is going correctly. I don't know if I have the right titles or anything like that. I am live on YouTube. Yes, I am. Selective coordination, a deep dive. There it is. Night at 5. So I'm good. I'm good on YouTube. I'm perfect. Oh, I think. Well, I am just went live, and I think I only go live on Thursday nights on my YouTube channel, but I've been having some difficulties here. Tommy D in the house, rocking it, you know it. Ryan Jackson, awesome. So I'm live and I'm in the house on YouTube, and believe it or not, it looks like I'm actually streaming to the other two platforms as well. So Facebook and LinkedIn. And Ryan, I'm starting a blog, or not a blog, a podcast. I got 2 podcasts. I think I'm going to drop one of them. But anyway, I'm learning, buddy. And I know, Ryan, you have your, you got to plop your link in the chat box for your site as well. I know you have a YouTube and all this other good stuff. So anyway, welcome everybody, and Ryan Jackson. We're going to be talking selective coordination tonight. We're going to do a deep dive, and I hope you have your coffee. I've got my coffee cam. Okay, I got Moby Cam 1 is on the coffee pot over there, and I tell you what, that is a really good coffee pot. It's got an insulated case. There's no heater on the bottom. It makes some doggone good coffee. It's OBX or not OB, it's OB something. I don't know the name of it, but anyway, really good. Okay, so tonight is selective coordination. We're going to dig in deep. I just got off the phone with Jody Wages down at the IAEI, and I was on a call before that, so I didn't have a chance to lose the tie and the jacket yet, but I'm sure within the next 2 hours, that stuff's coming off, and we're going to be digging into selective coordination, specifically looking at the single line diagram. There's MC. Good to see you here. Thanks for joining us, and we're going to answer some of your questions too. So I've got to find. I sent those questions to me. But up. Insulated case coffee pot. Yes, it is. It's a little bit different than a molded case. They're both listed to the same standard, but it's a little bit different than a molded case coffee pot, because a molded case coffee pot, you need to put a little burner underneath it. Good point, Ryan Jackson. Okay. I've got to find some of the questions. So I had a couple questions come in about selective coordination. I know we're going to get to them as we go through. So MC, keep me honest and on cue. So I'm going to be relying on you to help me do that. Let me turn my whiteboard off. And we are doing a live working tutorial. And we're going to be hitting selective coordination. So hopefully I got good audio. Ooh. And here's the other thing I'm doing, because I've got this podcast. I'm going to hit record on audio, and I'm going to take this and I'm going to post it on my podcast. I don't know about a 2-hour podcast, but you know what? Heck with it. All right. So I just turned on the audio for the podcast, and everybody out there in, I guess it's called podcast. Everybody out there in the engineering network or the Eaton Tech Talk land who's listening to this on Apple. So Ryan Jackson, I am on Apple, buddy. So if you go, I never thought it was possible. I got it up here. If you go to the podcasts on Apple, I am there. I did a bad one. You search for the Engineering Network and Eaton Tech Talk, all one word. But I'll tell you, I recorded one this morning just for giggles, and I don't know if the audio came out that well, but There it is. It's on. That one is on Apple. So you search for the Engineering Network, and I'm going to be maybe Ryan. I'll be calling you to do a little bit of tell me who you are. Excellent. You got to give me some feedback. I suck at this this whole podcast thing. I don't know anything about it, but all I do know is that people were asking for it. So I used Buzzsprout to get it done. I also have the other one, which is on what's it called? Anchor. So I have an Anchor thing too, which is a different platform, and I think the Anchor does the advertisings. But that one is on 6 platforms. It's on Anchor, Breaker, Breaker.audio, Eaton Tech Talk. It's on Google Podcast. That one. I mean, I'm on Google. I'm a Googleite. I'm a YouTubeite and I'm a Googleite. Pocket Casts and Radio Public and Spotify. So just more ways for me to get in trouble. Okay. Okay, so, but that's not what we're here to talk about. We're here to talk selective coordination. Now, selective coordination is a requirement in the National Electrical Code. Let's take a look at the definition in the National Electrical Code. I'm going to go to Article 100, and you have to look under coordination, selective. Coordination, selective. And don't go in, if you're in the 20 code, don't go to the medium voltage side. You got to go to the low voltage side and look for the C's. And I'm going to read to you what it says. Coordination, selective coordination. It says localization of an overcurrent condition to restrict outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent protective devices and their ratings or settings for the full range of available fault currents. And I mean, this is the you know what? I've never really read. This is the longest sentence I think I've ever seen. Let's just break this down a little bit. The first part is localization of an overcurrent condition. What does that mean? That means that the overcurrent protective device closest to the fault opens and nothing else. So from a selective coordination perspective, the goal is to isolate the fault without an extended outage in the facility. So, and that's good. So we know the philosophy. I'll call that the philosophical part of the definition of coordination. Selective coordination. And it says to restrict outages to the circuit or equipment affected. So, you know, the closer to the problem, the better off we are. Now it says accomplished by the selection and installation of overcurrent protective devices and their ratings or settings. So I have to pick the right overcurrent protective devices. And if you think, you know, we're going to be talking about this one-line diagram. So I have to pick the overcurrent protective devices that are in this diagram that helps me achieve my goal for localization of the problem. And I have to worry about the ratings. I have to worry about the settings, and we're going to talk about all of that. Now, the other portion of this says from overload to the available fault current. So overload to the available fault current. What does that mean? If you're familiar with a time current characteristic curve, time current characteristic curve looks like this. And I'm going to basically draw a thermomagnetic circuit breaker. Isn't that pretty? Man, I should have been an artist. So if you think about this, across the bottom is current. This up the side is time. So I have current versus time. And this is what we call a time current characteristic. And that is TCC. Now, there are a lot of people who say TCC is time current curve. And I'm telling you, you are wrong. It is time current characteristic. And then you have curve. That third C is important. And we debated that C at some NEMA meetings and IEEE meetings, Institute of Electrical and Electronic Engineers. It is a time current curve, but it is a specific characteristic of that device. And every device will have different characteristics. So don't underestimate the power of that third C. It is not time current curve. We all take shortcuts, okay? We all take shortcuts in a lot of different ways. Don't take shortcuts when we're talking about a TCC curve, because you're going to get me mad, all right? Don't want to get me mad. Time current characteristic curve. Now, the higher the current, what this is telling me, what this TCC curve tells me is, for any value of current, so let's say I have a value of current here, I know that this device will trip somewhere in between those two times. Those could be seconds, that could be minutes, depending upon the value of current. And what we know is, the higher the current, if this is 0 seconds, or actually it's not typically 0 seconds, and we're going to look at the time current characteristic curve, this is typically 0.01 seconds, okay? What I do know is that the higher the current, the faster the clearing time. C is yes in Spanish. No? That is correct. But you know, Robert, from Omaha, this C is for Spanish. That's not a joke, buddy. We're talking about the TCC curve, the time current characteristic curve. We don't mess around with the C's in TCC. So the higher the fault current, the faster the clearing time. And you know what we call that? An inverse time current characteristic curve. So it's an inverse TCC curve. And the reason we say inverse is higher the current, faster the faster the clearing time. The lower the current, the longer the clearing time. Now, what I will tell you is reuse. Nope, I don't want to do that. I want to do an insert, or no, I want to do home, slides, new, duplicate. Okay, so let's just, I'm going to see how good I can do here. All right, so this is what we call the time current characteristic curve, and how we started going down this road, if you would recall, is I was talking about the overload to short circuit. On a time current characteristic curve for a circuit breaker or a fuse or whatnot, this area of the curve, I'd say from here down, from about right here, where that picks up down, you're in the overload region, because you're in a long clearing time of this circuit breaker. When you get into this region, you're into higher fault currents, which are more than likely going to be a short circuit current. But don't get me wrong, just because you're in the overload region of this circuit breaker does not mean just because you're in the instantaneous region of this circuit breaker doesn't mean it's a short circuit. Let me explain myself there. Because you're in the instantaneous region of this circuit breaker does not mean your fault current was a short circuit. And why do I say that? Because what if my instantaneous is set so low that a simple overload trips the breaker? I may have missized my overcurrent protected device. I may have put a smaller overcurrent device than I need. Just because you're in the instantaneous region does not mean, by definition, that you are have a short circuit occurring in your system. It could still be an overload or a temporary overload. Maybe, and remember, what's the difference between a short circuit and an overload? A short circuit goes outside the path that it's supposed to travel on. An overload stays in the path. A good example of an overload, motor inrush current. Motor inrush current is a temporary overload, overcurrent in the system. It's an overload current. It's a lower current, not necessarily enough to not a very high fault current, because you're still impeded by the resistance and impedance of the circuit, because all your currents are in the path. Clearing time is everything. That's why all of this is a moot point if no maintenance is done. Absolutely, maintenance is key, and 70B starts next week on maintenance. I'm prepared. My task group 4 was completed today. Anyway, now, when we say overloads, when we're talking selective coordination, what we're talking about is this region of the curve. So I could, for example, I could have a TCC curve that has a molded case circuit breaker downstream, which is a BAB, and I could have an F150 upstream. So this is the F150, and this is the BAB 30. Can't write with this thing, but in any case, I have two circuit breaker curves. What you want to make sure is that you don't have an overlap in your curves in this region. And that's why in the definition we say from overload to short circuit, and your short circuit's going to be probably up in that region. You could have a short circuit current that's low enough from an upstream. It might be in the instantaneous region of this downstream breaker, but not in the instantaneous region on the upstream breaker. So you're in the overload region on this F150 for this short circuit current, but it's not an overload. Does that make sense? I hope it makes sense. So we say from overload to short circuit because in the definition, we are more concerned about helping you understand what current you need to selectively coordinate to. And that's where a lot of debate occurs. Typically, from an engineering perspective, when I look at power distribution systems, you have to evaluate overcurrent devices with regard to a current. You think about on bus A, the current, if I have a fault at transformer 2, let's say that transformer is out there. It's out there in a parking garage, right? Where it's at an airport, and it's at a parking garage where you return your rental cars, and somebody thinks that that's the key return, and they slap the keys down in the side of the transformer. And let's say that those keys drop down and they go across phases. Now I'm going to have a fault inside that transformer. Whatever fault current flows to feed that fault, remember, current is comprised of electrons, and electrons are party animals. Okay, when there's a party, when there's an event going on, they all want to get there. The fault current that flows through the conductor feeding that transformer is going to be comprised of the fault current that's flowing through the main on bus A, because I've got the utility, and the motor contribution. So what you have is this, right? So we have a transformer like this. We have a breaker here. We've got a panel. We've got a breaker, and we've got a transformer, and we've got a motor. And let's say this is the utility. I've got fault current that flows this way because, you know, they're party animals. I've got fault current that flows this way, and all of those combined flowing through that breaker down to the fault. So if I want to make sure that this downstream circuit breaker that's closest to this transformer where the fault occurs, I want to make sure that whatever the fault current is, it's flowing through that breaker, which is probably very close to the fault current that's flowing through the upstream breaker. I want to make sure that when they both see that fault current, only the downstream breaker opens and clears the fault. There is no way for me to tell you the likelihood. Remember, you got to think about likelihood of a miscoordination unless I do some evaluation to a fault current value. So I'm going to plot the upstream breaker's curve. I'm going to plot the downstream breaker's curve. And I'm going to say, I need to make sure that I have separation of curves in the overload region. And if the fault current is high enough that it's in the instantaneous region of both breakers, that's when you've got to jump through some hoops. And we're going to talk about how you solve problems with selective coordination. But my fundamental message is, you cannot, it is impossible, it is the laws of physics would cease to exist on your stove if you would say two devices selectively coordinated and you did not calculate any currents. Do you understand what I'm saying? I need to make sure that I evaluate two overcurrent devices based upon the current. Now, what I'm not showing, and here's another reason why, what I'm not showing on this trip, well, I am sort of. Let's do this. I'm going to open up the PowerPoint presentation because I am going to modify this slide a little bit. And here's what I'm going to do. Right now, you see I have C Control V. Okay, I've got 3 breakers now on bus A. And bus B, can't put another breaker underneath it. I know what I'll do. What I'm trying to do is show you that bus A and bus B could have more than one circuit breaker. And this was brought up by MC out there. What we don't show in the National Electrical Code, we put a diagram which looks very similar to this. It's a transformer. I don't know if we, in Article 700.20 something. Ryan Juction probably knows the exact section. There it is. Yeah, it does have a transformer. 700. Well, this is 701. 701.32 figure. And in 700, we have the same figure, but it's 700.32. So that's nice. We were trying to be consistent. But you'll notice in this diagram, we have a diagram that looks very similar to this, but we don't show multiple overcurrent protective devices off of bus A. So here's what happens. If I have a miscoordination between, I'm going to do this, I'm going to copy. I'm going to call this, see that? I'm going to call this breaker 2. And I'm going to call this breaker 1. So breaker 1 is the main in this bus A, this switchboard, because we've already identified it's a 2000 amp switchboard. breaker 1, which is the main in this switchboard, has to selectively coordinate with breaker 2, because if they don't, I'm going to lose those other loads. That motor's not going to be supplied with power, and the other any of the other feeder or branch circuits that are in this switchboard, they all lose power too if breaker 1, the main, goes out, and not just breaker 2, which feeds that transformer. So that's the whole purpose of selective coordination. Now, the figure in 700.32 and 701.32 and a few of the others don't show those other circuit breakers or overcurrent devices because they could be fuses. But the point is that if you have a miscoordination, then you drop more loads than what you would have if you would have coordinated. And what my point is, you can't make that determination if you don't calculate fault current. Now, the argument and the debate that I have seen in this world of selective coordination is, if I put an intentional delay on breaker 1, which is the main in the main panel board, to where my 3-phase bolted fault current is not in the instantaneous region of breaker 1, then I can guarantee you that the incident energy for that downstream transformer is going to, and breaker 2, now breaker 2 might be in the instantaneous region. That's a bad example. Let's say that remember we made a change in this one line diagram. Here, going to do, it's easier if I just draw it on the whiteboard. So remember, I have a panel with a main breaker in it, and I have a feeder circuit breaker that's feeding a transformer, right? And all of these are in the same. Now, the incident energy in that switchboard, that 2000 amp switchboard, is not dependent upon that main overcurrent protective device. Why? Because I got to think about line side propagation. If you don't know what that is, watch a previous edition of this. So what did we say about reducing the incident energy? A safety by design principle would be to pop that main breaker out, take the main breaker out of this panel board, put it in its own enclosure, right? So now the incident energy in this switchboard is not dependent upon the main, because I got rid of it. Now it's dependent upon the upstream overcurrent device, which is that device, which is in its own enclosure. But if I need to selectively coordinate breaker 2, which is the feeder going to that transformer, and breaker 1, which is the main, or would have been the main, but just feeding that 2000 amps switchboard, if I need to make sure that the fault current that both of these see is less than the instantaneous pickup of breaker 1, the incident energy, that tells me for sure I'm either in the short time delay band of that trip curve, which, remember, what's a short time delay? Remember, a trip curve for an electronic trip unit. When am I going to see an electronic trip unit? I can have electronic trip units all the ways down as low as you can go. I can have an electronic trip unit, but for a 30 amp breaker or a 50 amp breaker, 60 amp breaker, am I buying a multi-case circuit breaker with an electronic trip unit? Heck no. Why not? Well, I can buy something a lot less expensive. Okay. This is what a trip curve looks like for an electronic trip unit. It's very defined. The bands, the air bands, are much tighter. Now, if this was that upstream 2000 amp breaker and I wanted to selectively coordinate and I wanted to keep my currents out of the instantaneous region of both devices, then I would know my 3-phase bolted fault current is in that region, which is in the could be the short time delay region, which I can lower that down to like 0.07 seconds and give you a good lower incident energy. But it could be that I don't have a short time delay, and what I really have is something that looks like this without a short time delay, and now I'm into the long time delay and well past 2 seconds, and my incident energy just went through the roof. So what you're doing with selective coordination is you're trying to balance reliability and equipment damage And the reason is because as you move up into the power system closer to the utility, you're adding intentional delays. With circuit breakers especially, my delay, if I showed you two trip curves, and I'm just going to create a TCC curve here. I'm going to call this sample, and I know I'm not showing this right now, but bear with me. Patience. I'm going to, all right. I hear you yelling. So me with monitor 1. I'm going to create a new, I'm going to create a low voltage, not a fuse, because we're going to talk fuses. I'm going to do a thermomagnetic circuit breaker, molded case circuit breaker. I'm going to pick a library, and we said for success in anything you do, when you're in any of these libraries, there's a critical step that you can't forget, because else, if you don't make this step, everything else you do from here on in is all screwed up. I'm just telling you, it is all screwed up. The first thing you need to do is go to the filter on this library and look for where it says Eaton or Eaton Cutler Hammer or Cutler Hammer. You got to ignore all of those other words in there. So I'm going to grab a GHB circuit breaker. I've got to give it a voltage, a bus voltage, and we're going to give it a 480 volt. Whoa. We're going to give it a 480 volts. And watch this magic. You ready? Boom! It shows up. Okay, so the next thing I got to do to get me out of the way, I'm going to do this. I'm going to change the profile. Now this is the GHB circuit breaker. I'm going to go to TCC settings. I'm going to do this in multiples of times 10. So 10 on here is 100. 100 on here is 1,000. 1,000 is 10,000. And then the next thing I'm going to do is add another circuit breaker. I'm going to add a static trip, which means a static trip means it is a electronic trip unit. I'm going to give it the same bus voltage. And now I'm going to go and grab, remember, for success, telling you, if you don't do this, you're going to screw everything up. You need to go in here and filter this to Eaton or Cutler Hammer. We'll do this. Where's the Eaton at? There's Eaton / Cutler Hammer. So I'm going to put we'll do this one. This is a CHLD. It's an L-frame circuit breaker. This is electronic. So this helps you understand the difference between an electronic trip unit and a thermomagnetic circuit breaker. Okay, so look at the way these lines are. I'll get me out of the way. The instantaneous region is down here on the bottom. These curves are this is 125 amps, so that's a 63 amp. So what did I had a GHB. What's the amp on that GHB? The GHB is a 15 amp. So on this guy here, I'll make him 125 amps, and I'm going to add some delay, or let's even increase it a little bit higher. That's 240 volt. Let's see, we'll do a 480 volt, 250. There we go, 250. There we go. So now I'm moving the instantaneous. So you see what I'm doing. I've increased the size of this from say 125 amps, and look what the instantaneous did. And now I can't get that instantaneous to move any further to the right. Okay, so this is important, because selective coordination, I need to get separation of curves. But now remember, what I'm doing right now is I'm being the artist. An artist will look for separation of curves on a TCC. An engineer is going to realize I have to know what my fault current is. So the instantaneous region, Robert from Omaha, yes, there's no definition in the code, but the instantaneous region is where, remember, what is an instantaneous? There is a definition in IEEE, the IEEE Blue Book. It focuses on focuses on, this is the problem with two different keyboards. The IEEE Blue Book focuses on the molded case circuit breakers. And let me see if I have a copy of that on my, let me look for color books. Color books. There's red, there's gray, there's buff, there's brown, violet. Is it the violet book? No, there it is. Blue Book. That is circuit breakers. So I'm going to open this. I can't show it because it's copyright information. So I'm going to read it to you. Control F. And I'm looking for Instantaneous. Okay. Instantaneous trip circuit breakers. But up. Here's the scope. Instantaneous trip only. Here we go. Instantaneous pickup. Remember, when I say pickup, it is a current value. Because why? If you look at these trip curves, up across the bottom is current, and up the side is time. So pickup is what level of current will I pick up, right? Will the breaker recognize that I'm going to start to open? So instantaneous pickup is defined as the nominal value of current at which an adjustable circuit breaker is set to trip instantaneously. Instantaneous trip is a qualifying term indicating that no delay is purposely introduced in the tripping action of the circuit breaker. And this is, adapted from the NEC. It is in the NEC. Look at that. And the Blue Book had to remind me. If I go to Article 100 and I look at, and it says adapted from, so I think it's starting to come off. There's nothing in here. Let's see if there's anything that says instantaneous. H-I-N, no, I don't see anything that says instantaneous. There might be under circuit breaker. Let's just do a real quick. Under circuit breaker, conductor, commissions, class, circuit breaker, sorry about that. Circuit breaker instantaneous trip. A qualifying term indicating that no delay is purposely introduced in the tripping action of the circuit breaker. Thanks, Ryan. Jackson in the house. So the instantaneous region is no intentional delay. Remember that, no intentional delay. If you look at this trip curve, look at the black curve on here. And if you're colorblind, then it's the one that has the diagonal. It's not the swooping color. This, all right, now it's the blue curve. Now it's the black curve. So this, when I'm moving, look, I'm adjusting this. What am I doing? I'm adding an intentional delay. This is not the instantaneous region. This over here in this black all the ways over to the right, there is no intentional delay added. This clearing time of 0.01, 0.02, 3, 4, 5, 6, 0.07 seconds right here, and then you get into the real fast clearing time. All right, let me just let me explain something here too. So these trip curves, I'm an engineer. I'm an electrical engineer. Conservative. Engineers have to be conservative. What do I mean by that? I would rather have you overdressed for an arc flash event than underdressed. So I may estimate things to put the numbers a little higher. The engineers on products. Whoop, there we go. The engineers on products, like for this curve, that fat band that's 0.07 seconds, that tells you that it's going to trip somewhere between 0 seconds and 0.07 seconds. The reality of the fact is it's probably going to go a lot faster. Why is that? If you go to the time current characteristic curves from the manufacturer, I'm not going to call one up. We'll just go down to another rat hole. If you go to the TCC curves of a manufacturer, you'll find that they'll tell you that these curves are good for 50 and 60 hertz. These curves are good for from this temperature to that temperature. They'll give you all these qualifying factors. And you know what we do as engineers? We will publish a longer clearing time. We'll put fatter bands than what is reality, because we don't know if you're using it at 50 hertz or you're using it at 60 hertz. And sometimes what we'll do is we'll say, you know what, I can't plot both of those because the band would be huge. So I'm going to plot it at 60 hertz, but I'm going to tell you on the TCC curve that you need to adjust this if you're using it at 50 hertz. Or I was just talking to a gentleman who's working on a 400 hertz system. If you're at 400 hertz, your trip curve is going to change based upon the frequency that you're at. And where do you see 400 hertz? We see 400 hertz in minus 20 to 30% tolerance in the instantaneous region. There you go, MC. Thank you. So you'll see 400 hertz like in airplanes and stuff like that. So, but you've got to understand that there's bands, and you've got to read the TCC curves. The TCC curves have a lot of very important information. So what I'm showing you here is that this breaker is what? It's 125 amps at 63. Now, that's 125 amp frame. And it's a 63 amp trip. Way up there is 63. If I move this to 110 amp trip, look what moved. Okay, there's my amp trip up there, right? So that now at least you have the little, that's my pickup. And that's at 110 amps. I lower it down to 70. I bring it back up to 90. Okay, I'm moving, but now my instantaneous is adjustable. If I put it at maximum and I go down to 70, I can't bring my instantaneous. So it took the instantaneous with me. But if I go down to 63 amps, I am moving the instantaneous, which is rare. Question some things sometimes. So I can lower my instantaneous. Okay, I can raise my instantaneous. Sometimes I can't do that. And you're right. The left side of the band, it's the beginning and end of the error margin. So what we would say is on this trip curve for say this value right here is 197 amps. If I follow it up, it'll trip anywhere from 0.798 seconds to 1.589 seconds. Okay, and we use those two clearing times to help us. From an instant energy perspective, we always use that top end. But the band helps us figure out selective coordination. So if I tried to selectively coordinate this, I couldn't in the overload region, let alone the instantaneous region for the very high fault currents, because I've got an overlap of curves here. So what is my solution? In this case, the only solution I have is to increase the frame of this circuit breaker. So I take it from 125 amps to 250. What did I just do? I went from 125 amp frame to a 250 amp frame. What did I do? I could have changed the size of the breaker. I definitely changed the price of the breaker, right? I definitely did that, but I also gave myself a little bit of flexibility. So now in the overload region, I'll call it the overload region, which is these lower currents. In the long time, and this is what we call the short time delay. I can lower the short time delay. I can increase the short time delay. And you know what these are? These are dials on the circuit breaker. Okay, they're little dials on the circuit breaker. When I change, I rotate a dial, I could be changing the time, which is a delay, or I can be changing a pickup, which is a current value. So in this case here, I'm going to lower the short time pickup and raise the short time delay. I've adjusted this portion of the curve. I did not change instantaneous. I did not change the long time pickup. It is still protecting 125 amps worth of conductor. But what I've done is I've now destroyed my selective coordination for the fault currents in this region. So for that reason, you always have to plot these curves, especially in the world of circuit breakers. Fuses make our lives a lot easier, which is why the breakers and the fuse guys go and they argue all the time on this topic. Because all I need to do when I'm dealing with fuses, I just maintain a ratio, 2-to-1 ratio for the most part, but you got to look at the tables. And regardless of the fault current, always up to 200,000 amps, whatever the interrupting rating is, I know I selectively coordinate. So the act of selective coordination is basically finding the recipe for this region, the overload region, we'll call it the overload region, the short time delay region, the long time pickup region, so that I have separation of my curves. So I know for any current in the overload, say if I have 99.3 amps, 100 amps, I know that this breaker downstream, this red breaker, is going to trip. And the upstream breaker is going to hold its contacts closed at 100 amps. So if those two breakers see 100 amps, the downstream breaker is going to clear the fault closest to the problem. The upstream breaker is not. And we typically work our way up from the load all the ways up to the main. So if I looked at this one line diagram, I would start closest to the load. I'd go all the ways down here to this circuit breaker, this 30 amp breaker right here, this BAB 30. I would plot that one first, and then I would plot the one upstream, and I would do an evaluation of those two breakers. My upstream breaker feeding this 250 amp. Oh, the other thing is you got to remember, to MC's point, there are multiple breakers on this bus. I could have 5 30 amp breakers. Do I have to plot all 5 30 amp breakers? As long as they're the same breaker. If they're all BAB 30 amp breakers, then that's I only have to plot one. So typically, if I'm doing like and a lot of people will do these in training classes, we'll just pick the largest breaker, okay? We'll pick the largest breaker in the downstream and plot it against the feeder breaker upstream. That's just what we do. You would probably, if you're doing a full-blown study, you would have a lot more breakers on each of these buses, because you'll be doing load flow studies. You'll be doing short circuit studies throughout the power distribution system. So I'm not showing other breakers in this, but there would be other breakers on this panel. So I would pick this breaker, and then I would pick this breaker, and I would send those. I would say go to a TCC drawing, and I'll call this level 1. And I say new. Okay, now I've just plotted these two trip curves, which is breaker 1. That's the BAB is this one here. And then I have the breaker 2. The upstream breaker is a KD breaker, 250 amp KD breaker. And I have obviously clear separation. Could I have put a different breaker in here? Maybe. Let's take a look. Let's add a different. Now this is a 250 amp panel board. Let's go and grab a thermomagnetic circuit breaker, and we're going to grab a. This is 208 volts. I'm going to go to the library, and I'm filtered on Eaton Cutler Hammer, so that's a good thing. I'm going to go to, I'm looking for a 250 amp breaker, right? So I'm going to scroll down here till I get to 2. There's an HKB 250. Oh, I got thermomagnetic. Okay, thermomagnetic, I need 2. There's a 250. J frame. K frames are bigger than J frames. So J frames got to be cheaper than K frames. I'm less expensive than J frames. So I'm going to double click on that. Now this is a 480 volt breaker. Question, Mr. Ryan Jackson. Can I apply a 480 volt rated breaker on a 208 volt system? For anybody out there, can I apply a 480 volt rated breaker on a 208 volt system? And does it change the trip curve? Yes or yay or nay, saith thee. Okay, so I could have done this with a you bet 110.4. Sweet. The delay time is good. There's very little delay between us and YouTube. So why wouldn't I use a J250? Why wouldn't I use a J2? This is a 250. That's 70 amps. Hold on, I gotta get I got to get this up to 250, right? 250. Right there. Look, there's my 250. Look at this. And I can move the instantaneous way out there. Why wouldn't I use this? Why wouldn't I use a J? It works. It looks like it selectively coordinates. I mean, come on, right? JD, that's a JD breaker, right? MC, you got it right. That's a JD breaker. Why would I use a KD when I can use a KD electronic trip unit when I could have used a JD thermomagnetic? JD would have been less expensive. It probably fits on the same panel board. Cost, exactly. The price of the electronic trip unit would go up. Now, you'll say, well, heck, that BAB breaker, I've got separation all the way down to 0.01 seconds. Right, for you 0.1 second gurus. You know, I'm not going to make fun. I am going to keep it civil. We're going to focus on technical, right? So, 0.1 seconds. If you look in 517, Article 517 introduced 0.1 seconds. Now, if I had these two curves right here, I would say, you tell me, if you're brave enough, do these curves selectively coordinate? While I look for the section. Have I achieved, whether I use this one or this one, both of these are the same, so don't ignore this. Between these two breakers and the BAB, do I selectively coordinate? And I'm looking for the section while you give me the answers. I got MC says no. MC in the house says no. Is MC right? Is MC wrong? Ryan Jackson, my code guru, the walking code book. For the life of me, I cannot. I'm thinking about those two curves, and I know 517 dot what? 57. Not until you check the table. Okay. Why is that? So MC is saying I have to check the table. So now we're going to learn what the tables are. But what am I checking the tables for? I thought it was 517.17, but it's not. 517. I'm looking for coordination. Oh my goodness. Should know this off the top of my head. There it is. No, that's ground fault. It's ground fault. For full selectivity. That's right. I'm looking for full selectivity. For what though? But I need to compare something. When I go to the tables, I need one important data point. What is it that I need in that data point? 517.26. 517, that's what I'm looking for. Passed it up because I'm not. No. 517.26, Ryan. It says Article 700. It says 700. The life safety branch of the essential electrical system shall meet the requirements of Article 700, except as amended by 517. And it says 700.32, which is selective coordination, shall not apply. Thank you. 517.31G. Now that makes sense. G, there it is. Jeez, oh man, it's been a long day, and that's why we got Ryan Jackson. Put your website in there, Ryan. I'll make sure it gets out there. Overcurrent protected devices serving the essential electrical system shall be coordinated for the period of time that a fault's duration extends beyond 0.1 seconds. And it says in an informational note that the terms coordination and coordinated as used in this section do not cover the full range of overcurrent conditions. So what does that mean? That means, and what I tell everybody is what you need is your handy dandy selective coordination tool, and you hide everything below 0.1 seconds and you look for separation of curves. Because why? We don't care about fault currents. What MC has it right. What we are looking for is the available fault current that's passing through these two devices. And I have to make sure that I have to look at where the current is on this curve. So if I look at the one-line diagram, the one-line diagram says for this BAB 30, which is downstream of this KD 250, I have available fault current of 8,037 amps. Now, 8,037 amps, where is that on the TCC curves? 8,000, I'll show you where 8,000 amps is. There's 10,000. There's 9,000, and this is 8,000. So both of these circuit breakers are going to see a 8,000 over 8,000 amps. I'm into the instantaneous region of both circuit breakers. Based on this TCC curve, I would have to make a determination at the available bolted fault current that they do not selectively coordinate, because I would know. I don't know. What I can ascertain from the trip curves, because the fault current is greater than the instantaneous pickup of both of those devices, that the likelihood is there that based on the information available, they're both going to open based upon this information, the TCC curve. Now, we do have tables, okay? So I have with me, a huge spreadsheet, which I have not updated yet to our new trip units. I did, but this is not it. So, and that's why I picked the JD and the KD and the BAB. So I can go here, and I know I have down selective coordination tables, the way they work. And I'm going to tell you how we do it, which is a little different than what our competitors do. Down the left side, down the side of this spreadsheet is my downstream breaker. Across the top of this spreadsheet is my upstream circuit breaker. So if I zoomed out on this, down the left-hand side is my downstream device. Across the top is my upstream device. Makes sense, does it? I don't know why everybody else does it just the opposite. If you go to some other manufacturers, they put the downstream breaker across the top and the upstream breaker down the left-hand side. I'm just saying why you filter on Eaton. I'm just saying. So what I know in this scenario, I have a downstream breaker of a BAB, which is right here. This is a BAB 240 volt, 2-pole and single pole. And look, I have a 15, a 20, 25, 30, 40 on up. And yeah, somebody had commented that what if I go from, I added all of them here. So in my spreadsheet on our marketing literature on our website, we will jump from one to another. And we jump from one to another, and there's breaker sizes in between. So you always go to the larger. If for example, if I didn't show you the 30 and the 25 amp breaker here, and you had a 20 amp breaker, you had a 25 or a 30 amp breaker, you wouldn't use the 20 amp row. You would use the 30 amp row or the 40 amp row, whichever the next one up was, to cover the breakers that are in between. Now, what this table does, we have tested everything across the top with everything down the left-hand side. Now, some manufacturers will use the let-through, and that's a discussion for a different day on how that works. It's more of a mathematical and an analysis method to determine selective coordination at fault current values. But we actually tested, did a huge program. So what you're going to see across the top is my upstream breaker, down the left-hand side is my downstream breaker, and these values in the middle are values of fault current. So MC had it right. I need to, when I am looking at my trip curve, and I say I have a fault current that's higher than the instantaneous pickup of both of my devices, based upon the TCC curve, I would say they don't selectively coordinate. Now, I know a lot of engineers that'll look at these curves and say they selectively coordinate because I have separation all the way down to 0.01 seconds. Selective coordination is not about time. Selective coordination is about current and time. If I have to plot my bolted fault current value on here. Now, you may say, look, it's not a code requirement. And this is what I used to do. If I had a commercial or an industrial facility that wanted me to do a coordination study, I would plot the curves like this. I would plot my fault current, my bolted fault current, and I would put a little flag on my TCC curve. And if I was good at this, I could probably do it manually here, but I'm not going to because I don't know. I can't remember how to do it. But in any case, I'm not going to waste your time me learning how to use SKM. I would plot my available fault current. And then I would do an analysis. If my fault current was in the instantaneous region, I would tell my customer, all right, you don't selectively coordinate to the three-phase bolted fault current. I would calculate at the time when I was doing these, we didn't have 1584. So I would use the IEEE Red Book, and the Red Book would tell me what's the most common fault current in a power distribution system. It's the arcing ground fault. So and they would tell you the percentage values, and I would say, okay, based upon IEEE 242 or 141, whichever book I was using, they say the most common fault is an arcing ground fault, and based upon their references, it's 60% or 70%, whatever percentage is of the bolted fault current, and I would plot that number. And if that number coordinated, it was lower than the instantaneous region of the upstream device, higher than the instantaneous of the downstream device, I'd say, okay, look, you don't selectively coordinate to a three-phase bolted fault current, but you do coordinate to the arcing ground fault current or the ground fault current. And it's a level of assurance, but if you want 100% positive that under all fault conditions, you will never have a cascading event because of miscoordination, then I would say you've got to go to the three-phase bolted fault current because you know you're not going to get anything higher because that's the maximum available fault current. And it's probably a theoretical number that's higher than what you'll ever get because I'm ignoring some impedances. If you go back to that impedance diagram from my earlier classes, I didn't include the bus impedances. I didn't include overcurrent device impedances. I rearranged things I would rearrange things to show all my motors on to give me my maximum available fault current that I could possibly see. So if I'm coordinating to that, if I'm selectively coordinating to that, then I have a 100% assurance that I'm never going to have a cascading event. The moment you start coordinating to lower values of fault current, now you are making some guesses, right? I could use 1584, calculate the arcing ground fault current and plot that and say, look, you selectively coordinate to the arcing fault current. You don't selectively coordinate to the bolted fault current, but based upon your application, that might be enough. Okay, that might be the sweet spot that says, look, I'm not trying to create, it's not a life safety system. If I lose some coordination because I had a higher fault current than what I anticipated, I took a little bit more of my system out, I'm not going to lose sleep over it. But when you're talking life safety, Article 700, 708, 701, now you're talking, it makes a difference. And that's why those articles have elected to go to selective coordination. But outside of the requirement, it's really a design decision. Now, why would I pick one breaker over the other? Let's go back to the tables. What do I have? The thermomagnetic breaker was what? A J250, a JD250. So I would take the BAB 30. There's my BAB 30. I'm going to highlight this yeller. And I'm going to go over, remember I have 8,000 amps of a bolted fault current. I'm going to scroll to the right until I get to a number that is 8,000 amps or greater. There's my 8,000 amps. And that is a KD 400 amp breaker. I don't want a KD. Where's the JD? What do I have? I have a JD what? JD 250? Here's my JD 250 right here. Look what that tells me. My JD 250, 3,400 amps. 3,400 amps, anything greater than 3,400 amps, and I will open both breakers. Now, let's look at this, and this is how I go down the road of some people who will say, you should, 0.1 seconds does not consider any fault current value. And here's why I think that scares me. Now, remember, that's just a minimum requirement. We should be going above and beyond that bare minimum. And here's why. If I'm looking at a healthcare system, I'm looking at a hospital, I'm looking at a life safety system in a hospital, a critical system in a hospital. In this case, if I put a JD breaker there, yes, it doesn't selectively coordinate to the 8,000 amps, which you will say will never happen in a power distribution system. And so I say, okay, what about the ground fault currents? What do you think the ground fault currents would be? Are they 8,000 amps? No, they're not 8,000 amps. What are they? If you look at the red book and stuff like that, they're like, we'll say 60%, 70% of the bolted fault current, whatever that number is, or your arcing ground fault. You look at your arc flash, your 1584 calculations. I say, okay, you're saying it's around 60 or 80%. Let's say 50%. Let's just be a little bit more conservative. And I'm going to cut 8,000 amps in half as 4,000 amps. Based upon my tables, you're still going to trip for the most common fault in a power distribution system. So my perspective is, I'm sitting there saying, look, if you don't agree with a bolted fault current, if 517 healthcare lets you pick something different, my gut tells me you don't want to ignore fault current altogether. As engineers, as power systems engineers, we need to say, what fault current do we want to selectively coordinate to or coordinate to? If it's not going to be the bolted fault current, why don't I want to go to the bolted fault current value? Because look, or why might I not? It's all about cost. It has nothing to do with anything other than cost. Let's go to the 8,000 amps. I'm going to go to 8,000 amps. Where was 8,000 amps? Here's 8,000 amps, 400. If I picked a thermomagnetic 400 amp breaker, what did that tell me? What did I just have to do? If I said, I don't want an electronic trip unit, I'm going to pick a 400 amp breaker. I can't adjust this 400 amp breaker down to 250. What does that mean? Ryan Jackson in the house. I'd have to pick 400 amps worth of conductor. I'd have to put a 400 amp panel board in instead of a 250 amp panel board. So not only did I increase the size and the cost of that breaker, I've increased the conductor, I've increased the raceway, because the conduit, I don't know, whatever conduit or whatever conduit I picked, the size of that might not be adequate for 400 amps worth of conductor as opposed to 250. So now I got to pull different pipe in. I got to put different pipe, and hopefully I didn't find this problem after the fact. And oh, by the way, I can't use a 250 amp panel board. I got to use a 400 amp panel board. The cost of my system went up considerably, but that's for somebody who doesn't know what they're doing. If you investigate a little bit further, yeah, arc flash is going to be higher, right? Why is arc flash going to be higher? Because I have put in an intentional delay. Now I've increased the size of the conductor. You could say, well, fuses are your friend, Ryan Jackson. You could say that, and I'll show you what a fuse will do for you, and it'll bail your butt out of some problems. But in any case, and that's why I think, what's nice in my position, I work for Eaton. We make fuses and circuit breakers. I don't have to have druthers. I don't have to try to talk you into anything. We have to find the right recipe. But I've got a larger circuit breaker. You can make an argument to say, well, Tom, you increased the size of the conductor. The impedance of the conductor went down. The fault current went up. But your arcing currents are not going to be in the instantaneous. And look at this thermomag breaker. If I did this, if I pushed this instantaneous out as far, if my bolted fault current value was less than the instantaneous pickup, where's my arcing fault current? Is down here. I'm way in the long time region. My instant energy went through the freaking roof. It didn't just go up. It went through the roof. Okay. So the thermomagnetic circuit breaker solution is, I don't, when I start pushing it up, yeah, you're going to probably, I don't think you're saving money in the long run. You may spend less money on the breaker, but you're going to spend more money on everything else. Now, we're going to go up. We're looking for 8,000 amps. Here's another 8,000 amps. This is a 400 amp frame, 160 amp trip, KD breaker. So now I say, hey, and look where I can put this. I can put this in any one of these panel boards. Okay, I can put it as a main in my panel board 4. Is that the main? No, the main's the top row. I can put that in, where's 8,000? Right here. I can put, now remember, this is a 400 amp frame breaker with, it's probably the same breaker as this, but it has an electronic trip unit. I can adjust it down to 250, long time pickup. And look, I can have it as a main in a 1A, 2A, 3A, 3E, 4. You know what this means? 1A, lower dollars, 2A, a little bit more money, 3A, a little bit more money, 3E, a little bit more money, 4, you're looking at a little bit more money. So as you go up in these numbers, the dollar signs are going to go up, the more flexibility you're going to have. So this is the other aspect of selective coordination. When you're going through this process of picking these circuit breakers, make sure you're looking at what equipment you plan to buy, what steel, I call it wrapping steel around the breaker. What will it fit, and where in the panel board will it fit? Okay, so so I picked up, I got a BAB 30. I can do this one. I can't do this one. 8,000. That's going to trip on a ground fault current. What's the ground fault current? Let's take a look at the. Let's look back at SKM, and the ground fault current 6,799 amps. Okay, so MC had a question earlier today about what about ground fault currents? Do I have to coordinate those? Remember, ground fault currents are a zero sequence current. Yeah, we use zero sequence CTs and things like that, but they're real. They're real currents. And I can trip a circuit breaker, so I have to coordinate my ground fault curves with my overcurrent curves, and that's a challenge. It really is a challenge. But in this case, my ground fault current is 6,799. So I'd sit down in the healthcare world. I'll say, look, you're ignoring your ground fault current, which I know for a fact. I know because of testing that it's going to trip that thermomagnetic circuit breaker. I know for a fact. So picture yourself as an engineer on the stand. Somebody gets hurt, somebody gets killed or whatnot. And they're going to say, well, we had a cascading event. Did you know? Well, yeah, I did. Well, the code only requires this. That's what the minimum requirement is, but do you know better? Yes, I do. So it puts you in a sticky wicket. But I think 0.1 seconds puts a professional engineer in a sticky wicket. You can fall back on the fact that you say, yeah, 0.1 seconds is all I need to do. But the moment you have a cascading event, and especially if it causes a loss of life or hurts somebody, now you're into a sticky wicket. The other sticky wicket you're in, I've added delays. I've increased incident energy. Okay, now what I would typically do is advise my customer. I don't make that decision. So if it's not a code requirement, so in 0.1 seconds, if it's a healthcare, what I would do if it was my project, I would tell my customer, look, the code does not require you to do this. So coordinate to a voltage fault current. The code doesn't require you to coordinate to the ground fault current. The code doesn't require you to do any of this stuff. I can ignore fault current, but I'm telling you that if you want a more reliable power system, then I would recommend something. I would feel comfortable recommending that you coordinate to the ground fault current because it's the most common fault current in a power distribution system. I could feel comfortable saying, look, the likelihood of you getting a three-phase voltage fault current is low. Granted. And I took steps. I'm not required to go to the three-phase voltage fault current, but I know ignoring fault current is not a good thing either. So I went to a ground fault current, advised my customer of that. They said thumbs up, and that's what we went with. So I always say whenever it's coming down, especially if you have a PE license, fall back on IEEE references, fall back on code, fall back on something else to justify your engineering judgment calls. Ryan Jackson says, my experience in lawsuits is that the code matters, but the best practice or standard of care matters more. It's civil, not criminal. Exactly right, Ryan. So the challenge here is that, yes, the code says 0.1 seconds for a healthcare system, but the first problem that they tie back to this type of, a good example. It wasn't a healthcare system. Donnie Cook, Shelby County, Alabama. There, he calls me one day and he says, the jail just went down. And what happened was there was a fault on the roof. It took out the main for the facility. The transfer switch transferred, and then it transferred over to the generator. And then the generator breaker tripped. And he says, Thomas, why did that happen? Now, it wasn't our breakers, but he wanted to understand why it happened. So he walked down the system. He got me back. He got me the trip curves, and I plotted them for him. And I demonstrated. I showed him. I said, look, you know, you don't coordinate. You don't even coordinate on the ground fault currents. Nobody looked at that. Now, it's not a life safety. It wasn't an Article 700. It was a 702 system. It was an optional standby system. But his argument was, he says, all of these years, they performed maintenance on that generator. They cycled that generator. They started it. They fueled it up. They did all of this maintenance on it so that when they needed it, that it would operate and function. He goes, and it didn't function. He said, all that money was for nothing. And then he said, it was a prison, right? So then he goes, emergency procedures, you need to get everybody out into the yard. Well, all of the doors were on electric and they couldn't find the physical key. So you look at that and you say, you can't plan for the unexpected, but when the unexpected happens, that's when our design principles go into place to say, look, I thought about that. Yeah, it rarely occurs, but when it does, thank God you had that backup and you did the engineering up front. He did all the maintenance on his part. That transfer switch transferred, that generator started, and it worked like clockwork. It met the time limits that they expected, but they didn't coordinate, and it took out the generator. So there they were, trying to figure out what the heck happened. So coordination is important, and when the lights are out. For some, in this jail, they did not open when they lost power, and that was, I don't know if it's because of the age of the jail or the standards that they were built to, but that was, in their case, that was the issue, and they didn't have a physical key. So I don't know why. I thought the same thing as UMC, but his argument wasn't necessarily around the fact that they could not get them out. His argument was, look, I spent all this money in maintenance and it didn't amount to a hill of beans. So in any case, some level of coordination is good, and I think you always have to consider fault current. Now, so we know this guy is out from a selective coordination, so I'm going to destroy it. I hit destroy and it is gone from the system. So that is why I picked this breaker at 250 electronic trip unit. I based it upon the fault current that was at that point in the system, and I used the tables. Now, the reason I used the tables is because where is 8,000 amps? 8,000 amps is actually right here. Okay, well, I should just look at the tick marks. It's getting late. So this is my 8,000 amp mark right here. I'm in the instantaneous region of both of these breakers, but because of the tables, I know that I selectively coordinate to 8,000 amps. Oh, wait a second. What was my fault current? 8,037. Do I selectively coordinate to 8,000 amps? I'm going to roll it up. I mean, 37 amps. What's 37 amps amongst friends? Is 37 amps a matter of 10 feet? Let's see. Balance study, run. There it is, 10 feet. All I did was add 10 feet of conductor, and now I work. Think about it. There's different ways to solve this problem. I can increase the size of my upstream overcurrent protected device, or I can tell my electrician, go take a few laps around the block with your conductor and reduce the fault current. One-to-one transformers, beautiful, beautiful solution. Well, what does that do? One-to-one transformer, that adds another overcurrent device. You need to put a primary and secondary. It adds space, right? And cost just to knock fault current down. So maybe a little bit longer of a run if you can get away with it. Okay. There's different ways to address the selective coordination in regard to this. I can reduce the fault current by adding impedance into my system. I can increase the size of the upstream overcurrent protective device. But when you start increasing the size of the upstream overcurrent device, make sure that this long time pickup can be adjusted down to where you need it to be. And here is another solution. So I'm going to add a fuse. Ryan Jackson brought it up. Amber Alert, East Pittsburgh, Pennsylvania, Amber Alert, 2018 white Jeep Compass. Amber Alert on a white Jeep Compass. If you are in Pittsburgh, the license plate number is LPB 2547. Okay, so close that. I'm going to add a fuse, low voltage fuse, double click. Oh, I'm already there. All right, so I'm going to grab, since it's a 30 amp, and this is 208, I am going to grab what we call, and you always do this for best success. This is critical. If you don't do this step, everything else is null and void. You have to filter on busman. That makes everything good. You go down to TCF, and you grab the TCF fuse. And then now I'm at a 1 amp fuse. I need 30 of these puppies. There's 3, there's 10, there's 17.5. So I'm just going to go to 30. There's my 30 amp fuse. Now, if I go to, and I did not prepare this, I'm going to go to Eaton Busman selective coordination table. Whoop. Oh, it's got to be in here somewhere. So I'm going to do a search. Resources. Quick spec application note. Let's try this one. And I'm looking for a table where we tested fuses downstream of circuit breakers. I'm hoping that it's in here. This is the fuse table. Remember, so if I have a TCF fuse, there's the 2-to-1. Be mindful that depending upon the fuses that you have, it could be upwards of 8-to-1 or 4-to-1. What does that mean? If I have a 30 amp fuse downstream at a 2-to-1 ratio, as long as my upstream fuse is 60 amps or more or higher, 30 amps to 60 amps, the available fault current passing through both fuses could be 200,000 amps. And I will guarantee the 30 amp fuse will open and the 60 amp will not. Okay? Just because of the way, the current limitation. Here we go. Here we go. Look at this. Now you are going to go, Tom, this is the silver bullet. This is the silver bullet. Let's say I have a TCF. I had a 30 amp fuse. All of these have 30 amp fuses. I needed 250 amp, right? Check it, 250 amp fuse, upstream breaker. I've got a 200, maximum 400, 225. So K-frame. That's a 240 volts. What do I have? I have a K-frame breaker, right? But this is an electronic trip unit. A K-frame breaker goes up to 400. If I made it a 225 amp, I could put an F-frame breaker in there. If I had it as a 225 amp panel board, I could put an F-frame breaker in there. Selectively coordinates up to 65,000 amps. Why? Why is that the case? When I put this downstream, I could replace this device. If I put a TCF 30, I could go back and put in a thermomagnetic. We're going to make this, that breaker is at 208. What did we say it was? We said it was a, if I could do an F-frame 225, an FD 225, if I could live with 225 worth of panel, I could go to the library, and I could find an FD breaker at 225. We come up here to the largest one we've got. 225, 65,000 amps. That's a 225, not a 250. It's a 225 thermomagnetic breaker. Can I put a 250 amp panel board on a 225 amp circuit? Yes, I can. If I can live with a 225 amp breaker and a 225 amp panel board, I've just reduced the footprint. I've reduced the cost considerably. Now, the fusible panel board is going to be a little bit more expensive. I'm not sure of the price differences. But I have lowered my incident energy probably as well, because where was my fault current? Way over here in 8,000 amps. Think about that. I'm way into the instantaneous region of that breaker, that 225 or 225 amp breaker. I'm way over there on that breaker. So my arcing fault currents, my ground fault current was 8,000 some amps. I'm going to this fuse, and the reason it works that way is because the fuse acts so fast. I'm clearing less than a quarter of a cycle. So that breaker didn't even know the event occurred. What we don't show is what's plotted down here, and we don't have to when you have the tables. So in some cases, replacing the downstream device with a current limiting type of fuse, in our case, from an Eaton perspective, we've tested these things together. So we have a little bit of an advantage over others in the industry. But I can selectively coordinate up to 65,000 amps, which is the interrupting rating of that upstream circuit breaker. So the fuse can get you out of issues. Now, if I was going to look at this system and I was going to coordinate this, selectively coordinate this using all fuses, I mean, it's very simple. I have a 30 amp fuse here. I use a class J fuse. So as long as this is 60 amps or larger, I selectively coordinate up to 200,000 amps. I could put a 250 amp fuse there, be done. This breaker here, or this overcurrent device, just needs to be 500 amps or more. I have it as an 800 amp, so an 800 amp fuse selectively coordinates up to 200,000 amps. And then I could go up to, and we'll talk about going around a transformer here in a second. But so what I'm doing is I'm just starting from the furthest part, picking my overcurrent devices. If I'm using circuit breakers, they are current sensitive. I need to evaluate at an available fault current. If I want to make my upstream overcurrent device smaller and not an electronic chip unit, I can put a fuse downstream and use the tested pairs from our literature that shows, look, I can put a 100 amp fuse downstream of an FD 225 and selectively coordinate up to 65,000 amps. That gives me a lot of breathing room. And here's what that does. If this was a fuse, and this, instead of being an electronic trip unit, 250 amp breaker with a higher instantaneous pickup, remember, I need to selectively coordinate this breaker with this one. So the bigger that one is, the harder it's going to be for me to selectively coordinate. So let's look at this one. This is 12,844. I've got an 800 amp. I'm starting with a CKD. So let's go back to my table, CKD. I'm going to go to the left-hand side now. I'm going to scroll down to get to a CKD, the KD breakers, J, K. And that was a K-frame 250, right? So I'm going to highlight that yellow. And what's my fault current? Whoop. My fault current is, I'm going to use 14,000 amps. 14,000 amps. So now I got to scroll to the right to find something 14 or higher. Let's go 14. We're going. We're on a stroll. We're on a stroll. Whoa! I got 18. Here we go. Where does this take us? 18,000 amps. I'm into an ND. You know why that's? So it's an ND breaker. And look, I can do an ND 800, an N frame 800, and it's important to see where can I put it. I can put it in a panel board or a switchboard. I can put it into a Powerline 4 panel board, which is a big panel board. But you're going to be in a big panel board anyway, 800 amp feeder. So 800 amps selectively coordinates to 18, so I could put an ND breaker there. If I didn't want to use an ND, I could use an RD. That coordinates up to 35,000 amps. Okay, now let's say if instead of using the KD, I used the JD 225 because we said that would work and it was a thermal mag breaker. Now let's go and scroll over. Ooh, I can go to 30. Where am I at? Again, an ND. So that wouldn't have gotten me too much. Even if I used the fuse downstream, I would not be into a smaller breaker upstream. So these are the things you need to do. You need to look at the coordination between these breakers, and this is how you use the tables. Now we have an online app for this, Selective Coordination Designer. I put it this way. I read books. I love to have the book in front of me. I'm a paper guy. I'm not an electronic guy. Although I'm streaming to 3 different platforms and I got a podcast, I personally, I think the closer you are, the more you're using the tables as opposed to tools, the more you understand what you're doing. And the more you might be able to notice, instead of going to the tables, which will put you into a larger device, which may put you out of the bid, you might be able to engineer things and go, I can use this one instead because now you're more intimate with the process. You're more intimate. You know, we went through how to create the impedance diagram, how to calculate that, so you know what SKM is doing in the background. Okay. But on these selective coordination tools, it's important, I think, it's going to take you a little bit more time, right? But it's important to understand the tables. So now let's talk about real quick, what time is it? Geez, oh man, it's 6:33. I've been going for an hour and a half. My coffee, oh, it's cold. That was terrible. Cold. It got bitter too. All right. Anyway, maybe I think I put too much coffee in the coffee pot. Let's go take a look at Coffee Cam. There it is. There's Coffee Cam. Okay, Coffee Cam. Coffee Cam is not doing anything for us. Not doing anything for us. Just sitting there. Tool Belt Workshop. Can't went. You need to charge the closing springs on your coffee pot. Yes, I do. Absolutely. All right. So let's talk about around a transformer because it gets tricky. And I'm going to do this. I'm going to do this, and I'm going to throw up the whiteboard. And I'm going to do that, and I'm going to do that. Okay, I'm throwing up the whiteboard. So, transformer presents a challenge. Why? When you think about, I drew a line and I screwed up. David Smith. Okay, here we go. So I have a primary overcurrent device. I've got a transformer. I have a secondary main. And I have breakers downstream, right? Or fuses. So that's sort of my one-line diagram. Just want to get to all black. There we go. So think about a fault here, a fault on the secondary. And let's say, what is this? This is a 480 to 208 transformer. I have what's the fault current on the secondary? We're gonna use the numbers. We'll say 12,844 amps. Okay. So that fault, that three-phase bolted fault current at this point in the power system is 12,844 amps. So this breaker is going to see 12,844 amps. What current does that breaker see for that fault downstream? MC, Ryan Jackson, does the primary breaker, I'll call it A, see 12,844 amps of fault current during this fault on the secondary? I need we got a half. We got an approximate half, right? How do we know a transformer does not cease to do its job? The laws of physics do not cease to exist because of a fault current on the secondary of this transformer. The transformer will continue to do its job. What does a transformer do with the turns ratio? The IA, which is the fault current flowing through the primary breaker, is going to be equal to IB, the secondary, times 208 divided by 480. The turns ratio. So IA is going to equal 12,844 times 208 divided by 480. 5,566 amps. I'm going to trust you on that, MC. Okay, so that's the turns ratio. The breaker A, the primary breaker on this transformer, is going to see 5,566, while breaker B is going to see 12,844. How do I use the tables in this situation? Remember, my tables are made by shooting current through two devices at the same current. In this case, I don't have the same current going through both of those breakers. So my question to you is, can I use the tables in this method? Take my jacket off for this one. It's cold in this basement. I need to get flexible on this one. Can I use the tables? MC, yes, I can. Yes, I can. But here's the trick. Here's the trick. Now let's do this. I'm going to plot these curves. This is what I love. Absolutely love this stuff. Oh, why? So I'm going to, oh boy, gotta be careful. My whiteboard just got disappeared. Got too many computers, too many keyboards. So I am going to do this, me and monitor one. I am going to select all three of these breakers, and I am going to go to the TCC drawing. I'm going to call this, level 2. Okay, now this is my this is my primary breaker, and this is my secondary breaker. The primary breaker is not going to see all 14,000 amps or 12,844 amps. It's only going to see 5,566 amps. So where is 5,566 amps? 5,500. Oh, look at this. And 66 amps is just about, well, there's 5,700. Right here is 5,700. So now I know I am not way in the instantaneous region of this upstream device, but I am in the I'm verging. I'm almost in the long time delay. I'm in that, I call it no man's land, that band that goes all the ways up. I'm right on that cusp. So when I go into the tables, I'm going in with, what's my downstream device? My downstream device is oh man, what is it? It's an NG breaker. That's an NG. It's an N frame breaker, right? So I can go into this table on the left-hand side because the downstream is an N. Just scroll down. There's my N, and it is a what? Was that my 800 amp breaker? Yes, it's an 800 amp breaker. So there's my NG. There's my NG breaker, right? So I've got to scroll over, not to 12,844, because the upstream device is not going to see 12,844. The upstream device is only going to see 5,566 amps. So I'm going to scroll over until I get to 5,566, which is not on. When voltage changes, you multiply high side by the transformer factor. Yes. It's exactly right. Wait a second. I transpose my secondary current because remember, I did my math. I know what my fault current is going to be on the secondary, and I would transpose that to the primary. So my N frame breaker, I don't have the tables. I can't leverage my tables on this regard because I don't have a tested pair that's downstream. Look at the table values and then multiply by K. Yeah, you could do that. You could do that. So I've got 5,000 amps, and now what I could do, here's the other thing I could do. Let's go to Eaton.com/TCC. And I'm going to go to molded case circuit breakers. And I'm going to go to the N frame. I'm going to look at the ND breakers. All right. So I'm really getting deep in the hoopla here, because now I'm going to the actual TCC curve, and I'm not using SKM at this point. I've popped out of SKM. So I need an 800 amp frame breaker. There's my 800 amp frame. And these are my instantaneous. Let me just look at my trip unit. Ooh, what trip unit did I have? Let me look at my SKM. I had a 310 plus trip unit. So 310 plus, 310. There's a 310. I'm just going to see if there's a 310 plus. 10, 310, 310 plus. There's my 310 plus, and there's my 800. So there's my frame rating, 800 amps. Whoa, my 800 amp frame. And now I come into, and we don't show you what goes down on below 0.01 seconds. So I am somewhat in a little bit of a sticky wicket, because I'm at 5,500 amps. I am right here. I know that I would feel comfortable, but I would have a hard time picking that breaker. I don't know if I can't move the instantaneous over. So my fault current, my 5,500 amps is about right in here. Man, that's going to be a tough one. That is going to be absolutely a tough one, because my table does not. I'd have to look at my newest tables to see if we, and that is an ND breaker. And I don't know why we did not go anything less. An ND 800 downstream of, what did I pick? I picked, what's this? I picked an LD on the primary. Okay, let's do this. An LD breaker. So let's do it this way. Let's go to the LD breakers. An LD. I've got 5,000 amps. Where's my LD what? I've got an LD 600, HLD 600. So there's an HLD 600. I'm going to just color this one a little bit different. And yeah, we did not test that. So I've got to pick a different breaker. Can't pick my ND. Ooh, ooh. MC, it is getting late. MC, it is getting late. I've got the wrong two breakers. Where did I screw up? Jeez, oh man. I don't care about this breaker and this breaker. I don't care because I lose the same load. What I should have plotted. Oh my goodness. Let's do this. Which breaker should I have plotted? Or do I care? No, I don't. That's the main. I need to plot this guy, the CKD 250. So that's PD 009. Let me do a new or existing and pick PD 009 and hit OK. Man, does coordination through the transformer really matter? Yes, and here's why, Brian. I don't care about this 800 amp breaker with this 600 amp breaker. Why not? Because I lose the same load if both of them open, right? But if I have this 250 amp feeder breaker, has to selectively coordinate with this 800 amp breaker, because I can have multiple breakers. I could do this, right? I could throw this guy. I could throw. I could do this. I could have this guy. Okay. If a fault downstream of PD9 or right here, say right at the load terminals or whatever, if that causes the main breaker to trip up here, then I take out the transformer and I take out all of these other breakers. So you have to understand all of the breakers. Now, if there was just one breaker in that panel board, I could say, yeah, you don't have to worry about it. But I have to selectively coordinate this 250 with that breaker. Boy, MC, thank you. I was going down a rat hole and I was wrong. I'm like, what the heck? I don't get it. Why am I having such a hard time here? So there's my PD9. It has to selectively coordinate with this. Now this one is a KD. So if I go back to the KD, oh my god, man, I can't believe I went down that road. That was a rookie mistake. So I go to a KD, but it is 649. So here's my KD breaker, right? And I said 225. Did I pick? No, I picked 250 because that's the electronic trip unit. There's my, I have to go over to 5,500 amps. And where's my ND breaker? Is that primary and ND? This an ND? That is a, what is it? It is an LD. It's an HLD. It's not an ND. It's an HLD breaker. So that breaker is an HLD breaker. If I go to the LD breaker up above, an LG, LD, and I believe it was what, a 600 amp? Yeah, so there it is there. If I go down to my LD, which should be highlighted right here, 10,000 amps. I selectively coordinate to 10,000 amps with that breaker. I'm good to go because I've tested. The downstream breaker is my JD 225. I selectively coordinate to 10,000 amps. So for this guy here, remember this breaker here was the KD 225. That's my branch or feeder breaker in the downstream panel. I don't have to worry about breaker B, the primary device on the secondary of the transformer, with the first device on the secondary of the transformer with the feeder of the transformer, because if both of them open, I lose the same load. But for a fault at here, if the KD 225 does not selectively coordinate with the device A, which was an LD, that was an LD what? That was an LD 600 amp breaker. Then I would take out more and I could lose all those others. So the 225 needs to be evaluated with that primary LD circuit breaker. And in this case, I know it works because I only have to selectively coordinate to 5,500 amps, and I'm good up to 10,000 amps. So that's how you go across a transformer. You don't have to worry about the two, and that's an exception in the code, but you do have to worry about these breakers down here, and you would use the fault current. Now, if you say I'm going to coordinate to the ground fault current, then you coordinate to the ground fault current, or the arcing fault current, whichever one you have to do, okay? And that is what gets you to your selective coordination, and you would do that all the ways up through the system. Yeah, so you could work so MC, you could work it either way. What I did was I took the fault current and I transposed it to the primary and didn't change the table values at all. Or you can multiply all of the table values by the turns ratio of the transformer. However you want to do that, and then still use the secondary fault current, the 12,844. Whichever way feels comfortable for you, then that's what you do. And that's the nice thing about math. You can skin a cat two different ways. So that's basically what happens when I'm selectively coordinating through a transformer. So Ryan, what you have to think about is not the main in that secondary panel board. You have to think about the feeder breakers that are down in the bottom. Okay, so MC, you've got your math right. You're absolutely thinking about it correctly. I did it just the opposite way, but we can both get to West Virginia by two different routes. All right, perfect. So, okay, so let's do this. So now I helped you understand. Remember, these are the primary and secondary breakers. This is the downstream breaker. And what I'm not liking right now is this is my 225, right? That's my 225. Is it my 225? Settings. That's my 250. It's a 250, right? And this is my 800. But I've got to move, there it is. So I've got to move I need separation. So I know based on the tables that these two breakers work for the fault current at the secondary, but my problem was I was overlapping in the short time delay. So I'm going to move that up. I don't have to worry about that inrush because the inrush is based for the primary of the transformer. This is my primary. So there's my three breakers. And this is what I would typically do. I would show the transformer damage curve. And I would probably, instead of doing current times 1, I would change this to current times 10, right? And you could plot the thermal damage curve for the conductors on here as well. And there was another question that I got on YouTube in TubeLand. The question was, the question was, I'm just going to go and go to Studio here and go to comments. And I have to unselect that. So the last question I got was, regarding the cable selection, you selected the cable according to a cable ampacity and you didn't check the cable short circuit capability. So how do we check to make sure that we're protecting the conductor when we're selectively coordinating? Because this is all a part of it. Now, one is obviously I'm picking my thermomagnetic breakers for the long time pickup, and if I plot my cable damage, so I'm going to plot a cable here. What's get a cable, a conductor, conductor 6, CH6. So I go to I'm going to say existing, and I'm going to go to cable 6, and there's my damage curve for cable 6, which cable 6 is the breaker on the secondary of the 250 amp breaker. And if I look at the trip curve for my 250 amp breaker, that's this guy right here. My cable damage curve is way over here on the right. Typically, your cable damage curves are going to be way over there on the right. Rarely have I ever run into a case where I followed the code, picked the right size overcurrent device. I don't think I've ever had that case, and did not protect the conductor. I still would plot the conductor damage curve, and remember, this curve is calculated, and really what we're looking at is the damage of the insulation, not the what do you call it, the annealing point or vaporization, right? So my breaker's going to trip fast enough, and it's thermally protecting, and it's protecting that conductor from short circuit faults as well. So hopefully that answers the question that I got on that one. I hope I answered that question. I'm just going to take a look real quick at any. MC had a bunch of questions, and showing my, I don't want to show my email. Geez, oh man, let me do this. Let's just do, let's do me. Okay, so, hold on, I gotta find email, because there were some good questions. What's the interpretation of all upstream breakers? What does that mean for the code? So all upstream breakers. Now, I've heard people say, remember, 6 times the conductor full load amps is protected from the thermal damage. Absolutely. So remember, in the National Electrical Code, in Article 700, I got 2 minutes, but I might go over. 700.32 says 700.32 says all upstream overcurrent protective devices, right? So bear with me. 700. So 701 is all similar language. It says selective coordination shall be selected by a license. Legally required standby systems, overcurrent devices shall be selectively coordinated with all supply side overcurrent protective devices. That doesn't mean you have to call the utility and hope they selectively coordinated everything in their world. Remember that Article 700 and 701 only applies to, say, 700. Okay, let's just talk about the Article 700. Okay, in a selectively coordinated system, in an emergency system, Article 700. Let's just draw a. I've got a utility. Got a panel here and a panel here, basically. I got a generator, and I have a utility, and I have a breaker, and I have a breaker, and then here, right? And that's my transfer switch. And I have a breaker here. So this is my normal side, right? So that's normal. And this is life safety. But technically, the life safety system is right here. Okay? Now, the way the language reads, it says that the overcurrent devices shall be selectively coordinated with all supply side overcurrent devices. This device, what are all supply side overcurrent devices? That would be this guy, and if there's one up here, that would be that guy. Also, that would be this guy, and if there's a main, which hopefully there is, it would be that guy. So this circuit breaker on the secondary of the transfer switch, which is on the life safety side, or the 702 side, 701 side, or the 708 side, this is in the life safety system, or it's on the legally required standby system side. The requirement is for that device to selectively coordinate with all upstream devices, which would include your feeder and your main on the normal side. But your feeder and your main on the normal side do not have to selectively coordinate with each other. Why? Because those two devices are not in the Article 700, 701, or 708 system. 700 does not have purview over those two devices. It does have purview over the devices that are in the life safety system. So the onus is that the device downstream of that transfer switch has to selectively coordinate with what's on the normal side. Not the devices on the normal side don't have to selectively coordinate with each other because they're not in the Article 700 system. But that device downstream of that transfer switch does have to selectively coordinate with what's on the normal side because those are upstream. And if you can get it, so the way panel 13 looks at it is, if you can get it done without changing the devices on the normal side, then, great. But if you have to change those devices on the normal side to make sure that the device on the emergency side selectively coordinates with those, then so be that too. So that's what they mean there. All right. So hopefully that answers that question. I'm going to read another one. I don't see mention of 0.1 or 0.01 seconds selectivity in the NEC. Correct. Now, in some specifications, and this is what really irritates the bejeebers out of me, I will see specifications that say you must coordinate or coordinate to 0.01 seconds. And you go, what does that mean? Does that mean my BAB breaker, which goes down to 0.01 seconds, that you don't have to worry about fault curve, that you can just cut the curves off below 0.01 seconds and ignore fault current because it's not defined anywhere. It's not in the code. It's not in any IEEE documents. It's not in any technical reference that tells you what to do. So what I've learned is when people say 0.01 seconds, they mean selective coordination because in their mind, it's all currents and all times. It's all times because people forget about current. You have to evaluate the breakers with regard to current. So 0.01 is not in the code. 0.1 is in 517, like we discussed. And that is basically ignoring fault current. And you're hiding all your curves, all of the overlaps below 0.1 seconds, and just looking at the pretty pictures and saying, do I have space? And that's all you have to do. You don't have to calculate fault current at all outside of interrupting rating. So if you have two ground fault settings, then you can coordinate like phase currents using TCCs. What about when it is the first level of ground fault? Do you have to coordinate with phase? Yes, you do. That is the hardest part because think about what a ground fault current is. A ground fault current is going to have all your current's going to be flowing from, say, phase A to ground. The overcurrent device that's going to have to compete with the zero sequence relay or the ground fault sensor that's in the device upstream is going to see that current too. And if you don't coordinate at that ground fault current, then for the ground fault device, then yeah, You've got to think about it. The only time you don't have to worry about it, I would argue, is when you're downstream of a delta to Y ground. So if you have a delta to Y ground, the zero sequence currents aren't going to flow through the delta because of symmetrical components, but you're going to still see fault currents flow, but you won't have to worry about the zero sequence CTs upstream aren't going to activate because the zero sequence currents are isolated because of that primary delta. They won't circulate. They'll circulate in the delta, but they won't. Your upstream devices will not see a zero sequence current because of that delta Y ground. So an isolation transformer, a delta Y ground transformer, helps you eliminate the issues around ground fault GFPE. What breaker would you use if you are high amp breakers in a panel? I'd have to really go through and plot those curves. MC, Mahesh, I'd have to plot those curves and see where that knee of the GFPE is. And this is why, what do people do? We drive it up as high as we can with the longest delay. In fact, we just changed our circuit breakers to give you a full 1 second delay. And what does that do to incident energy? Which is why ground fault protection of equipment is there in the first place. It's there to reduce the incident energy and prevent the burn downs that were occurring. And that's why it went in the code. So we are intentionally putting delays and defeating the purpose of that device. Ground fault protection for generators. Do we need 2 levels? I believe they got away with this requirement. So the requirement for 2 levels, I think you'll find it in 517. If you have it on the normal side, you're not required to have ground fault protection like in a healthcare system. And in a 700 system, it is, I believe, optional. But you're not allowed to trip. Let's take a look. To indicate a ground fault on a solidly grounded Y emergency system of more than 150 volts or 1,000 amps or more, the sensor for the ground fault sensor, so you can provide indication on the life safety side, but you're not allowed to have ground. You're not allowed to trip. So you can put indication. I can't remember exactly which section that is in. It is man oh day. Oh, I'm in article. I'm gonna look in article 700. So 700. There is transfer equipment, the ground fault, and it says the sensor for the ground fault. I'm in 700.5, 700.6D, and it tells you. The sensor for the ground fault signaling devices shall be located at or ahead of the main system disconnecting means for the emergency source, and the maximum setting, and again, it's 1200 amps for systems with multiple emergency sources connected to the paralleling bus. The ground fault sensor and the system bonding jumpers shall be permitted to be at an alternate location. So they're giving you those requirements to make sure that you are counting all of those ground fault currents. So yes, I believe it's 517 that requires 2 levels on the normal side. So 517, I'd have to 517 dot something, 517, yeah, 517.17c. That's where you're required. So on a healthcare, you have to have 2 levels on the normal side, but you're not going to be putting it over there on the other side. All right, that's all that's all we can think of for now. So, all right, so it is 7:09. I went 9 minutes over my little 2 hour, and now we didn't talk about arc flash reduction in light of selectively coordinating, but we did like for this system, we did run the arc flash studies, right? And how there's a couple different ways because we are going to electronic trip units. You can use the arc reduction maintenance switch. Yeah. Boom. We're done, right? Steve Cavaleris, thank you for joining us, buddy. So I could, since we're in the electronic trip units, I could put arc reduction maintenance switches up there. 708.52b also has 2 levels. Thank you, Matt Rabasi. I appreciate you dialing in, buddy. And thank you, MC. Thank you very, very much. Thank you very much. So, but on these breakers, you could put the arc reduction maintenance switch on those, and on your larger equipment up here at the service entrance, you can use technologies like arc quenching technologies that help reduce the incident energy. Zone selective interlocking can help reduce the incident energy, reduce the amount of damage. So we have ZSI, arc quenchers, arc reduction maintenance switch, and this is why I always say you can have your cake and eat it too, because you can get selective coordination. You could put technologies like arc reduction technologies, arc quenching technologies, and have low incident energy to provide protection for the electrical worker. So there are things you can do to help provide reduced damage and still get your selectively coordinated system. But you should always remember about the arc flash incident energy. All right, everybody. Real quick before we go, I need to coffee cam. The coffee cam is still working. It's still over there, and it's empty. So thank you for joining in. Sohrab, Alamos, thank you very much. Thanks everybody for joining in and participating tonight. And I accidentally streamed to Facebook and LinkedIn, and I didn't want to shut it down. So we were out on both of those platforms. And, you know, I did not at all look at the LinkedIn. I didn't even have it open. So I don't know if I see questions coming in from LinkedIn or not. I don't even know if I'm on LinkedIn Live. I thought I was. Yeah, I am. I'm live. I'm live right now. So, how do I see that? Oh yeah, by using the, whoa, okay. All about short circuit current for both. And I'm gonna make sure that I was getting those questions over here. George, Corey, thank you for, what about if the fault currents after the branch breaker? Yep, Tef, hopefully that was, but using this fuse is according to IEC standards. Is according to IEC standards. So from an IEC perspective, international perspectives, they have what they call they have selectivity. They call it discrimination in the IEC world, but there are tables there as well. Remember, a breaker is a breaker is a breaker. All you need to understand is, from a table perspective, and whether you're using fuses, the ratio tables will apply regardless of current. I don't care if it's current flowing in Europe, current flowing in Japan or Yugoslavia, wherever it's at. It's if you maintain the ratios, yes, you will have selective coordination. What about the short circuit current for both? Should be the same condition. Hopefully, I got all those answers. Thanks for joining in on LinkedIn. And I didn't check Facebook either. So I'm just going to take a quick peek before we close shop. And don't forget, everybody, please check out my podcast, and also check out podcast, and check out my YouTube site, which you're already on, hopefully. But if you're on Facebook, you may not be. What else I got going on? I got a lot of stuff going on. All right, so there's my Facebook stuff. I don't see any questions, so that's a good thing. So I don't think I missed anything. All right, everybody. Thank you, MC. Thank you. When voltage changes, you multiply. So I'm just looking. Ryan Jackson, thanks for joining us, buddy. Appreciate it. Mathur Abbasi, Sohrab, thank you. And LinkedIn user, thank you. Okay, everybody, I'm heading out. I got to go upstairs and get something to eat, take a break. We'll catch you, I don't know, maybe not tomorrow. I think I'm going to be drained. But if I do go live tomorrow, it's going to be something special. So I think I'll have to. See you next week. Next week, I have 70B meetings. Tuesday might not be a good day to have me go live during lunch. Me and David Smith are going to be going live. So we're going to have a little planning meeting tomorrow, figure out when we're going to be talking. So Atef, thank you very much. And thanks everybody out there for joining in with us. And thanks for what you do for the electrical industry. Thanks for what you do for the electrical safety. And please stay safe. All right. Take care, everybody. I'll let you, what we'll do is we will we're going to fade in on, now we'll just do, I'm not going to fade in on the mobile cam. I'm going to fade in on my closing. Take care, everybody. Stay safe. Be good. Right. We got it done.